Hello everybody. So this is a task sheet for percentage yield, um, and as you are probably familiar with from GCSE, percentage yield is a measure of how efficient a reaction is. So if we have a high percentage yield, that usually means that the reaction is very efficient. Okay, so there's not a lot of waste. But when we have a low yield, it's a reaction that's very wasteful. Okay, so we don't get as much of the product as we can. So the closer the yield is to 100%, the more efficient the reaction that has been carried out is. Okay, and the lower the yield, the more wasteful we have been. Okay, now percentage yield is dependent on many things. Okay, in general, in wider chemistry, you can get a relatively high percentage yield if you are very well versed in the practical aspects of chemistry. But a low yield is also very easy to get if you make a few mistakes. Now, the first thing is looking at this question here. Okay, so all the percentage yield is the actual amount that we produced. So if you look at this question, Aaron has made 0.42 grams. Okay, but the theoretical yield that was calculated using an equation, so this is the max amount that Aaron could have made, of 3.24. Okay, so we divide so we're dividing the actual by the theoretical, okay, and we're timesing it by 100. Okay, so 0.42 times 3 divided by 3.24 times 100 is going to give us 12.96% to 2 dp. Okay, so that's that. Now, state 3 potential reasons why Aaron's reaction had a low yield. Okay, so there's quite a few reasons for getting a low yield. Okay, so you're not going to get away with saying that Aaron's not very skillful in the art of chemistry, but you will need to say things along the lines of that the reaction did not go to completion. The reaction could potentially be reversible. Okay, now reaction being reversible makes the reaction very susceptible to conditions. Okay, whether that be temperature, pressure. So that usually ends up resulting in a low yield if the conditions are not controlled, which most reactions are not monitored and controlled conditions. Another thing could be that the products are actually difficult to separate. Okay, so you might have more than one product in a reaction, and the two products might be very difficult to separate. And the last potential reason could be that products are very difficult to remove from the apparatus. So in chemistry, you might form a sticky product that might stick to the bottom of your flask, your round bottom flask, or any other reaction vessel, really. So it's hard to scrape out all your product, and that leads to waste. So that's some of the reasons. I'm not really going to write them down, but yeah. So moving on to this example here. Okay. So this reaction, this question in general is almost telling you your balanced equation. So it's saying that we've got 2 moles of hydrogen which react with 1 mole of oxygen to give 2 moles of water. So from that, you should pick up straight away that we're going to get our equation, balanced equation, which is something along these lines. Okay, so 1 mole of oxygen, and it gave us 2 moles of water. Now, that's our balanced equation. Okay, so the actual amount that was produced in this reaction was 20 grams. So that's the actual amount that was produced, 20 grams. Okay, so 20 grams was produced. But what we want to calculate, okay, what we can calculate using this equation is the maximum mass, so the theoretical amount, okay, that we could produce from this reaction. Now, the theoretical, aka the maximum amount that we could produce of water in this reaction, okay, would be termed the theoretical yield. Okay, you can call it theoretical yield or you can call it theoretical amount. The more scientific way is yield, but I think for the purpose of understanding, theoretical amount and actual amount are better to use because they help you avoid confusion. So let's say the theoretical yield slash amount would be equal to, we'd have to use the equation of moles equals mass over mR. And then we'd rearrange that to find the mass. So mass equal to Mr times the moles. Okay, now once we have this, we can find the mass of H2O. Okay, now some of you might be thinking, well, we've already got the mass of H2O, it says it here, but no, again, remember this is the actual amount that was produced in the reaction, but to find the percentage yield, we need to know the theoretical amount. That's what we're calculating here, and this is the actual amount. We're calculating the theoretical amount. So mass equals Mr. So what's the MR of water? Okay, so it's one that you should really have to memory by now. The MR of water is 18. Number of moles of water, they've said it in the equation, 2 moles of water. Well, in the question, sorry, 2 moles. And as a result, 18 times 2 gives us 36 grams. So that's the theoretical that we should have formed. Okay, so that's just... Okay, so that's the theoretical. So once we've done this, we can write the percentage yield. Okay, so our actual amount was 20 grams. We got that from the question. The theoretical amount was 36, and we times it by 100. So 20 over 36 would give us a percentage of 56%. And that's our answer. So that's what's going on there, guys. So task 2, again, relies on the same principles. Okay, so we've been told that 3 moles of hydrogen react with 1 mole of nitrogen to give 2 moles of ammonia. So 3 moles of hydrogen. Okay, don't forget state symbols. React with 1 mole of nitrogen to give 2 moles of ammonia. Okay, 2 moles of ammonia. Now, if we take a careful look at this, you'll probably be familiar from the lesson that this is the Haber process. Okay, and it's famously one of the reactions of very high yield. Now, the Haber process itself is very famously a reversible reaction. So what we should have here is something like this. Okay, now let's have a look at this now. So percentage yield. So again, we've been told that only 8.5 grams was formed, and from that we can take that this is the actual amount. Okay, so it's the actual amount that we made. So, but if we're going to calculate the actual mass of ammonia that we made, we need to use mass equals the MR times the moles. Okay, now we're working it out for ammonia, so mass of NH3 is equal to the MR of NH3, which is 17, times the moles, which in this case we said that there were 2 moles of ammonia. So 17 times 2 would give us 34 grams. Therefore, the percentage yield could be easily calculated by dividing each other So it'd be 8.5 grams divided by 34 grams multiplied by 100, and that would give us a percentage yield of 25%. Okay. Now, in the grand scheme of things, this might seem like a low yield, but for a reversible reaction, this is quite a good yield. Okay. Most reversible reactions, they usually have a percentage yield of below 10, usually actually in the range of between about 5 and 8%. The thing is, this Haber process is very well studied, and the conditions, the pressures, the temperatures can be controlled to ensure that we produce as much NH3 as possible. Okay, the grand scheme of things, this is still low, but due to it being a reversible reaction, this is pretty good for a reversible reaction. So now let's move on to this one. Okay, now PB is lead, so this is lead nitrate. For those of you who've been paying attention in class, you know that these are polyatomic ions, because we've got in brackets, and the ion is made up of the NO3, so the nitrate ion is made up of more than one atom. Now, we're going to do this by having a look at, again, the equation. So we've been told that 1 mole of PbNO3, so lead nitrate, was reacted with potassium iodide to form lead iodide and potassium nitrate. So what we're going to do is we're going to write down what is going on. Okay, for clarity purposes, I'm going to omit the state symbols, but please put them in. Okay. Now, all right. Now, if we quickly take a look at this, what you'll notice is it's not balanced. So, iodide. So we've got 2 iodines on this side, 1 on this side. So we're going to stick a big 2 in front of there. Now the potassiums are now unbalanced, so we're going to stick a 2 here. Now, if we look at that, hey ho, we're doing well. Okay, it's all balanced. Now, we were told that only 399.23 grams of lead nitrate were formed. Okay, so that is our actual amount. Okay, so now we need to calculate the theoretical amount of lead nitrate lead iodide that is formed. And again, we do the same principle, same reactions as before. Same equation as before. Mass equals Mr times moles. So the MR of lead nitrate, lead iodide is going to be 207.2. Okay, and then we've got two iodines or iodides. I do beg your pardon. So that is 461. That's the MR, grams per mole. So the mass is going to be equal to the MR, which in this case is 461, times the number of moles. From the question, we can dictate that we had 1 mole of lead nitrate formed for every 1 mole of one mole of lead iodide formed for 1 mole of lead nitrate. So then it would be mass equals 461, which is the MR, times the moles, which is 1. And that is a lovely 461 grams. So then, just to finish it off, to work out our percentage yield, we would divide what we got actually, which was 399.23 over 461, times that all by 100, and we're doing well. And the question, we're going to give it to 86.6%. Yeah, that's fine. 86.6%. Okay, now task 3. Okay, now put a little box saying, is it balanced? Okay, just a little prompt for you. 3 grams of iron filings are burnt in air to give iron oxide. And then the equation's been given for you. Now, I've asked the question, is it balanced? Well, is it? No. And the way we would look at balancing it is, how many oxygens do we have? We have 3. Here we have 2. Now, what's the lowest common multiple between 3 and 2? It's 6. So we'd put 2 here to make 6 oxygens. We put 3 here to make 6 oxygens also. But as a result of doing that, we've now got 4 ions on this side. So we need 4 ions on this side. Now determine the moles of iron in a 3 grams of metal. Moles of iron. Okay, so we know that moles equal to mass divided by mR. So the moles of Fe are equal to the mass, which is 3.0 kilograms, all over the mR of iron, which if I remember correctly, is 55.8 grams per mole. We would get a number of moles as 0.0537634. So now that we know the number of moles of iron, okay, as this much, what we can do as a result is manipulate this and use our molar ratios to find out the theoretical amount of this that could be formed. Now remember, theoretical amount is the maximum amount that we could form. Okay, it's not the actual amount that we perform when we're practically doing an experiment, but it's using the principles of chemistry and conservation of mass. It's a maximum amounts essentially that we can form. Now, to do so, okay, we need to find out the moles of Fe2O3 that we could potentially form. Now, if we look at our handy dandy equation over here, we know that the molar ratio between iron and iron oxide is 4 to 2, okay, which is essentially the same as 2 to 1 if we simplify the ratio. So what we would have to do is divide this, the number of moles of iron, which is this, by 2 to get the moles of iron oxide. Okay, so how do we get from 4 to 2? We divide by 2. So as a result, the number of moles of iron that we're going to have are, okay, get ready for the number, 0.02688172043. Okay, note how I have not rounded. Okay, so now we know that the moles. And note how I've not rounded this number, okay, because it's going to play an important part in calculating our final answer. So you never round before you actually get your final answer. Now we know that the theoretical amount, we know the number of moles of iron oxide. Now, to calculate the theoretical amount, or the theoretical mass, we'd apply the same equation as before. Mass equals Mr times moles. Now, the MR of iron oxide is 55.8 times by 2, okay, because we've got 2 ions, plus 3 times oxygen, which is 3 times 16. And what we would get as a result of adding all these brilliant numbers together is a number we would get 159.6. Okay, and now what we can do is we can plug that in. MR is 159.6 times the number of moles, which in this case was 0.268817204.3. And once we've plugged all these numbers into a calculator, what we would get is 4.29 grams. And that is our theoretical amount. Okay, now the last bit of the question is calculating the percentage yield if 3.6 grams of iron oxide is made. So we know the theoretical amount, which is 4.29. We know that the actual amount produced was 3.6. So 3.6 divided by 4.29 times 100 would give us a percentage yield of 83.9%. Lovely. Okay. So some questions. Okay, so question 1 of task 3 is totally very similar to what we've done previously, but there's just a few twists to this. Okay, so we've got this equation firstly, all right? That draws my attention. Is it balanced? Well, no, straight away, because we've got an imbalance of sodiums here, and the sodiums are not balanced, okay? And neither are the oxygens and the hydrogens. Now, to balance this, what we're going to do, okay, we're going to focus on balancing the sodiums first. So we put a 2 there. Now the sodiums are balanced. Now, as a result of that, the hydrogens are now imbalanced and the oxygens are imbalanced. And to counteract that, put a 2 here. As a result, this equation is now fully balanced. So we've been told to calculate the percentage yield. Okay, now the only actual mass, so you might be thinking to yourself, well, what do we use? We've been given a lot of masses. Okay, so what do we actually use as our theoretical amount and what do we actually calculate for? Now, in this case, it's been stated that as a result, this many grams of this much was sodium sulfate were formed. Okay, so we need to calculate our percentage yield using this. Now, piece of information that we've been given is that 4.7 grams of sodium hydroxide had been used in the reaction. So what we can straight away get up to is we can calculate the moles of NaOH. Okay, so remember, moles equals mass over MR. So in this case, we've got a mass of 4.7, and we've got an MR of 23, which is for sodium, 16, which is for oxygen, 1 for hydrogen. Now, those of you who are a bit quick on maths, that would just be 4.7 over 40. And that would give us a lovely answer of 0.1175 moles. Okay, not a huge number as we were expecting before on the previous slide, previous question where we had a number that was 8 or 9 digits long. Okay, it's good. So now that's the moles of sodium hydroxide. Now, if we look at our molar ratios, what we can now do is we can work out the moles of sodium sulfate. Now, to calculate the moles of sodium sulfate, we use our molar ratios. Now, our molar ratio between sodium hydroxide, which we've just calculated the moles for, and sodium sulfate is a 2:1 ratio. So what we would do is we would divide this by 2, our moles of sodium hydroxide by 2, to find out the moles of sodium sulfate. And our moles of sodium sulfate are 0.05875 moles. Now we know the moles, okay? As you're probably well aware by now, we can find the mass. So mass in this case would be the mR times the moles. Okay, you're probably sick of me saying this by now, but mass is equal to Mr times moles. Now, firstly, we need to find the mR of sodium sulfate. Okay, so the mR of sodium sulfate is 142.1. Now, I'm going to save you the working out. It is 142.1 grams per mole. Now, what we can do is finally calculate to the mass. Mass equals Mr, which is 142.1, times by the number of moles of sodium sulfate, which are 0.05875, which would give us a mass of 8.34375 grams. Okay, so this is our theoretical maximum mass that we could have formed. Okay, but the reaction has told us that we actually formed 6.04. So what we do to calculate this yield, okay, divide this by this to get, and then times by 100, 22.3 degrees. So it's our actual theoretical. That is one of the best options ever. This is one of the easiest ways to do it, is make sure that you label it if you ever do get confused, because there are a lot of numbers involved. Okay. And we end up with 72.3 to one decimal place. Okay, so one decimal place. All right, now that is that for that question. So for this one, it's again very similar. Mg plus HNO3 plus magnesium nitrate plus hydrogen. Now, this equation isn't balanced. How are we going to balance it? We're going to put a 2 here. And if you want to pause the video and check, that is balanced. So 40 grams of magnesium was reacted, but only 1.7 grams of hydrogen was produced. So we're going to do this percentage yield in terms of hydrogen. Okay, so first things first, moles of magnesium. Moles of magnesium are equal to 40 grams divided by its MR, which is 24.3 grams per mole. So 24.3. And that would give us a moles of 1.64609.053. That's the moles of magnesium. So the moles of hydrogen would be the same as the moles of magnesium, because there's a 1-to-1 ratio between the two. So moles of H2O, H26460 moles of H2. So the mass of H2 we can now calculate. So mass of H2 would be equal to MR of H2, which would be 2 times by the number of moles. And that would give us 2921 grams. Then percentage yield would be our actual, which was 1.7, divided by 3.2921, both in grams, times by 100, which would give us 51.6% to 1 decimal place. Okay, so that's the video, guys. See ya. Peace.